In this video, we're going to look at several examples that involve the integral test for series. Recall that the integral test states that given a series, if the associated function to that series is positive, continuous, and decreasing on the interval 1 to infinity, then both the series and the improper integral of that function will either both converge or both diverge. When we have such a series, we can easily check that these three properties hold, and then we can simply compute the improper integral to determine whether it converges or diverges, and then use the integral test to conclude the same behavior for our series. In our first example, we'd like to determine whether the series from n equal 1 to infinity of 1 over n cubed converges or diverges. In order to use the integral test for this particular series, we need to look at the associated function f of x equals 1 over x cubed and ensure that it has the three properties that the integral test requires. First, we need to check whether this function is positive on the interval 1 to infinity. And since this interval consists only of positive numbers, 1 over the cube of a positive number will always be positive, and so f of x is positive on the required interval. Next, we need to determine whether it's continuous from 1 to infinity. We notice that this is a rational function that is defined everywhere except x equals 0, and therefore the function is continuous everywhere except x equals 0, and in particular on the interval from 1 to infinity. Last but not least, we need to check whether the function is decreasing. Here we know that as x gets larger in the positive direction, our function is going to get smaller and smaller because we'll have 1 over a larger number, and therefore our function is decreasing. So since our function 1 over x cubed is positive, continuous, and decreasing on the interval 1 to infinity, we can use the integral test on this particular series. This means we want to compute the improper integral from 1 to infinity of 1 over x cubed dx. And once we determine whether this integral converges or diverges, we can conclude the same behavior for our series. This improper integral, by definition, is going to be the limit as b goes to infinity of the integral from 1 to b of x to the negative third power. And we can rewrite the function like this so that we can easily antidifferentiate it with the power rule. So we want to compute the limit as b goes to infinity of the antiderivative of x to the negative third power, which will be negative 1 over 2x squared, or negative 1 over 2x to the negative 2 power. And of course, we want to evaluate that from 1 to b. And so we want the limit as b goes to infinity of negative 1 over 2b squared plus a 1 over 2 times 1 squared, which will be 1/2. When we take the limit as b goes to infinity, our first term here will go to 0 since that denominator will get very large. And so we're left with just the limit of the constant 1/2, which is equal to 1/2. And so therefore, our improper integral converges because we get an actual value here. It converges to the number 1/2. And so based on the integral test, we know that our series will have the same behavior. So the series n equal 1 to infinity of 1 over n cubed is going to converge by the integral test. There is one small caveat that we have to be careful about here. It is true, certainly, that our series converges by the integral test, as we've just claimed. However, we don't want to claim too much. We do not want to claim that the series converges to 1/2, being the value of our improper integral. This is not necessarily true and is almost certainly not true. So while the improper integral converging to 1/2 gives us what we need to conclude that our series converges, it's important to remember that the series does not converge to the value of the improper integral. The integral test just says that the behaviors of our series and improper integral are the same. So that if our improper integral is a finite value, like it is in this case, where it's equal to 1/2, then our series would be equal to a finite number as well. And so the series is converging. but not necessarily to the same value as the improper integral. For our next example, we want to determine whether the series from n equal 1 to infinity of n over 3n squared plus 1 converges or diverges. If we want to use the integral test, we first have to consider the function f of x equals x over 3x squared plus 1, which is the associated function to this series. Certainly, this function is going to be positive from 1 to infinity, since both the numerator and denominator will give us positive numbers. It is certainly going to be continuous as well. We can quickly check in the denominator that this function will always be defined, and a rational function is always continuous when it is defined, and therefore this will be continuous from 1 to infinity. And this function is also going to be decreasing from 1 to infinity because the degree in the denominator is larger than the degree in the numerator, and so the denominator grows more quickly than the numerator will, leading to a decreasing function when we have positive values of x. And so here we have a series in which the integral test applies, and so we can proceed by computing the improper integral from 1 to infinity of the function x over 3x squared plus 1 dx. In order to compute this integral, we know that we want to compute the limit as b goes to infinity of the integral from 1 to b of x over 3x squared plus 1. And now we need to find an antiderivative for the function here. In this case, we can do a substitution where u is going to be the denominator, 3x squared plus 1. Du will then be 6x dx, the derivative of 3x squared plus 1. And since we only have an x dx in our integrand, we're going to replace that with du over 6. So du over 6 will be x dx. With all of these values substituted in, we're going to get the limit as b goes to infinity of 1/6 times the integral from 1 to b of 1 over u du. 1 over u is a function whose antiderivative is known. So this is the limit as b approaches infinity of 1/6 of natural log of absolute value of u evaluated from 1 to b. We do need to remember that 1 and b are values of x, and therefore we need to go back to the variable x before evaluating. So we have the limit as b approaches infinity of 1/6 natural log of the absolute value of 3x squared plus 1 evaluated from 1 to b. And we could certainly lose the absolute values there, since 3x squared plus 1 will always be positive for positive numbers like 1 and b, or we could keep them, doesn't matter, doesn't make any difference in this case. So here we have the limit as b approaches infinity of 1/6 times the natural log of 3b squared plus 1 minus 1/6 times the natural log of 3 times 1 squared plus 1, which is 4. So here we have 1/6 natural log 3b squared plus 1 minus 1/6 natural log of 4, and then we want to take the limit as b approaches infinity of that. If we look at our first term in our difference, as b goes to infinity, 3b squared plus 1 will go to infinity, and therefore the natural log of 3b squared plus 1 will go off to infinity. And since our second term in the difference is just a number, this entire limit will go to infinity, and so our improper integral diverges. And so here we have a divergent improper integral that corresponds to our series. And so our conclusion is that the sum n equal 1 to infinity of n over 3n squared plus 1 will diverge by the integral test. If you'd like to try an example, you can pause the video and determine whether the series from n equal 1 to infinity of 1000 over the square root of 2n minus 1 converges or diverges. You can resume the video, and the full solution will appear in a few seconds. We first check to ensure that the function 1000 over square root 2x minus 1 satisfies the requirements for the integral test. This function will certainly be positive from 1 to infinity. It will be continuous and decreasing on that interval as well, and therefore we can apply the integral test. Here we need to compute the improper integral from 1 to infinity of 1000 over the square root of 2x minus 1. We can rewrite the improper integral as a limit as b approaches infinity of 1 to b of 1000 times 2x minus 1 to the negative 1/2 power dx. We can make a simple substitution of u equal 2x minus 1, which makes du equal to 2dx and du over 2 equal to dx. When we substitute that into our integrand, we'll end up with the limit as b approaches infinity of 1 to b of 500 u to the negative 1/2 du. An antiderivative of u to the negative 1/2 will be u to the 1/2 multiplied by 2. And so we're left with the limit as b approaches infinity of 1000 times 2x minus 1 to the 1/2 power evaluated from 1 to b. When we evaluate it at b, we get 1000 times 2b minus 1 to the 1/2 power. And when evaluating at 1, we get simply 1000. As we take the limit as b approaches infinity, the first term will go off to infinity, and the second term, of course, is just the number 1000. And so our entire limit is a divergent one and equals infinity. Since we have an improper integral that diverges, the conclusion for our series is that the series will also diverge using the integral test.